Here are solutions to homework set number 3 for ECE 376. This homework set looks at binary inputs, binary outputs with a PIC microcontroller. The first problem is, suppose I have a thermistor. The resistance varies with temperature. Design a circuit that outputs 0 volts when the temperature is less than 5C and 5 volts when it's more than 5C. So I want to have a circuit that does something like this. Go between 0 volts and 5 volts. Well, the trick to do that is first for the thermistor, find the resistance at 5 Celsius. That turns out to be 2566.99 ohms. A PIC can't read voltage, or can't read resistance, but it can read voltage. So let's convert resistance to voltage using a voltage divider. Somewhat arbitrarily, I'm going to use a 2.2K resistor. So there's your R over R plus 2200 times 5 volts. This is 2.69 volts. So what I want to do is switch at 5C, which corresponds to 2.69 volts. In terms of plus or minus, as temperature gets really hot, I want the output to be high. So when this is really hot, R goes to 0. The voltage goes to 0. If I connect the minus input, then VP is more than V minus. I get the right answer, it's 5 volts out. If I get it wrong, just flip the plus and minus. So here's the circuit. And what this one does is when the temperature is below 5 Celsius, the resistance is bigger, the voltage is more than 2.6. When V minus is more than V plus, it slams low, 0 volts. So this is cold. When it gets hot, above 5 degrees Celsius, this goes to 0, Vn drops below 2.69 volts, V plus is more than V minus, I slam high. So there's the VI characteristic for this case. I can then take that to your PIC processor, and it now knows the temperature. Is temperature more than or less than 5 Celsius? Problem 2 looks at how do you add hysteresis. What I want to do is something like this. I want to turn on at 5 Celsius. I want to turn off at 0 Celsius. So same trick as before. Convert temperature to resistance with the thermistor. Convert resistance to voltage with the voltage divider. So that's this part of the circuit right here. I want to turn on. It turns on. Turn on at 2.69 volts. Turn off at 3.00 volts. So here's what it kind of looks like. I want to turn on at 2.69 volts, turn off at 3 volts. Since T on, or V on, is less than V off, I connect to the minus input. Here's my Schmidt trigger. The on voltage is your offset, and the gain is the slope. Output changes by 5 volts as the input changes by 0.3 volts, gives you a gain of 15.88. Make this ratio 15.88 to 1, and make it large. What's happening is this is actually in parallel with R. R is about 1K. 1K in parallel with 250K is still about 1K, a little bit off. So these points will be a little bit off. If I want to split hairs, I could add a buffer. That's this circuit. What a buffer does is the input impedance is 4 gigaohms. The output impedance is ideally 0. This can drive 50 milliamps. They can drive 250K. That'll make it more accurate. Usually I don't really worry about that because if I have 5% tolerance for resistors, this changes the resistance by 1%. Who cares about 1% when you're dealing with 5% tolerance resistors? Problem 3. In your lab kit, there should be a Piranha RGB LED. So that's what the LED looks like. This is actually 1 pixel of a scoreboard. It's got a red, green, blue LED in one package. Here we are. To power it, what I do is I connect it to power and ground through a resistor, like so. If I want the PIC to control it, instead of connecting to power, connect to one of the pins on the PIC board. Like if I do port C pin 2, pin 1, pin 0, the PIC can turn these pins on and off by setting these pins high or low. And with that, I have a 7-color flashlight. What the resistors do is they limit the current. Suppose I want to limit the current to 20 milliamps. That's what the LED is rated for. To find the resistance, I just do calculations. For the red LED, the voltage drop is 2 volts. This is 5 volts. Gives you 3 volts across the resistor. 3 volts at 20 milliamps is 150 ohms. For the green and blue LED, their voltage drop is 3.2. When the pickup is 5 volts, the difference is the voltage across the resistor. 1.8 volts at 20 milliamps is 90 ohms. So this circuit should turn on the Piranha LED, and actually this right here is the actual Piranha LED. I take one pin tied to ground. The other 3 pins I tie to your PIC board through 3 resistors. When the pin turns on, I get 20 milliamps. 20 milliamps turns on the LED. Now if I need less than 5 volts, less than 25 milliamps, the PIC can drive it directly. If I need more than that, I need a transistor. So problem 4 looks at the star LED. So this is what the star LED looks like. It's got a 6.8 ohm resistor built in. I connect it to power and ground, and actually 5 volts and ground, and it turns on. So if I want to drive it directly with a PIC, the star LED actually draws 330 milliamps when powered at 5 volts. The PIC can't drive 330 milliamps. For the PIC to drive it, I need to drop the current. So make it less than 25 milliamps. That's what this resistor does. This could actually be anything between like 200 ohms and 1K. Actually 100 ohms works. I just chose 1K because I had one of those lying around. If I make this 1K, then the current through the LED is the PIC outputs 5 volts. This is a 3 volt drop. Again, that comes from the data sheets. This is 3 volts at 330 milliamps. The way diodes work, the voltage-current relationship kind of looks like this. If it turns on, the voltage is roughly constant. So at 330 milliamps, it's 3 volts. At 2 milliamps, it's roughly 3 volts. The current then is the voltage drop across the resistors divided by the total resistance, 1.98 milliamps. To get the brightness, it's proportional. 330 milliamps is 200 lumens, so 1.96 milliamps is that percentage of full current. That percentage of full brightness, 1.2 lumens. And this is what that looks like. So I've got my PIC board. It's got a random program that's just counting. Send one of those numbers to your resistor. There's your 1K, the LED going to ground. You can see the LED is turning on and off. That's about 1.2 lumens. Not real bright, but you can see it. If I want to measure what's going on, take your trusty voltmeter. If I measure across the LED, and actually I'm going to change this to a pin that's always on. A lot easier to measure DC. If I measure straight across the LED, this should be, okay, let's just take it straight to 5 volts. Taking it straight to 5 volts, so I don't have the dang thing turning on and off on me. Going straight across the LED, this is your 3 volts. And I'm actually getting a lot of glare. 2.62 volts. Now for an ideal diode, the voltage drop is constant with current. Diodes are not ideal. They're close, but not quite. So as the current drops, the voltage does drop. It went from 3 volts down to 2.6 volts. The current, if I measure the voltage across the 1K resistor, measuring it backwards, is 2.29 volts at 1K, 2.29 milliamps. So that all checks out. I've got about 2.2 milliamps, well, about there. A little bit different because this curve is not really straight up and down. If I take the input then, and instead of going straight to 5 volts, connect it to your favorite pin on the PIC processor, you see this. The PIC is turning the LED on and off. Not real bright, 2 lumens. but the PIC is limited. It can only do 25 milliamps. Suppose I want to crank up the power. If I want to have full power across the LED, I need a buffer. That's the transistor switch. So here, the first thing I'll do is connect the LED from power. Let's blow this up. I'm going power to ground. Make sure the LED works. Yep, it works. Now instead of going power to ground, I'll go power to collector on a transistor. The base I'll take through a 1K resistor to my PIC board. So what happens is when this is 5 volts, that applies power to the base, that turns on the transistor, the light turns on. When this is 0 volts, it turns off the transistor. Now I've got power, a really bright light. That's what transistors for. They crank up the power. If I want to find out how the LED behaves, the thing's really bright, I will take the base resistor right here, take it straight to power. That turns the LED on all the time. It's really, really bright. Measure the voltage drop across the LED again. Measure the voltage across the 6.8 ohm resistor. And what I get is, for calculations, the base current is 5 minus 0.7 over 1K. This is a diode. Voltage drop across the silicon diode is 0.7, 4.3 milliamps. The collector current is 5 minus the 3 volts across the diode, minus 2 volts across the switch, ballpark, gives me 264 milliamps. To check to see if saturated, kind of two ways. Is beta IB more than IC? In this case, beta IB is 860 milliamps. I only need 264 milliamps. 860 is more than 264. Therefore, I'm saturated. That's one way. Another way is measure the voltage at the collector. So let's do that. So here's my circuit. It's turned on, really, really bright. The middle pin is the collector. This is the emitter. The voltage drop, VCE, is 0.022 volts. Now to saturate, I want the voltage across the transistor to be close to 0, but not quite. It won't be exactly 0. In electronics, we say when you're saturated, you're roughly 0.2 volts. I measure 0.022 volts, which is better than what it should be. It's close to 0, but not quite. It is saturated. And I wind up with the PIC, able to turn the transistor on and off. So here the base is tied straight to 5 volts. If instead I tie the base to a pin from the PIC, like right here, you can see the LEDs turning on and off. I've got my finger over it to dim it. I have an LED controlled by a PIC at 330 milliamps. That's what a transistor does. It's an electronic switch. Moving on to problem number 5. In problem number 5, I want to output a single note, 98 Hertz. What that means is I'm going to take a pin and toggle it over and over again. The wait time between toggles is n. That's 10 million divided by 2 times Hertz. The reason for 10 million is the PIC executes 10 million instructions per second. The 2 is there's 2 toggles per cycle, and the Hertz is what you want. So 98 Hertz is I should have a wait loop that's 51,020 seconds long. The main loop is I'm just going to count on port C. That causes it to set, clear, set, clear, set, clear on RC0. Wait 51,000 clocks, then repeat. To get to 51,000 clocks, I've got a wait loop. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This takes 10 clocks to execute. 10 times 100 times 51 is how long this takes. So that's 51,000 clocks. plus, this is 1, 2, 3, 4, plus 1 for go to, 5 times 51, plus 1, 2, 3, 4 per go to, plus 4. So total number of clocks is 4, plus 4 times 51, plus 10 times 100 times 51. It's actually 51,260, split with 51,020. If I try that, what I will see is, here's the same circuit I had before. This is causing the light to blink at 98 Hertz. I can't actually see that. Connect that to a frequency counter. There's the frequency, supposed to be 98, it's actually 97.67. A little bit off, just because it didn't get N exactly right. If you want to see it blink, this is what counting does in port C. Each pin is divided by 2. So first was 98 Hertz, here's 48 Hertz, 26 Hertz, should be have that 13 Hertz, see the light blinking, 6 Hertz, 3 Hertz. Anyway, that's the light blinking. If instead of having the transistor turn an LED on and off, I replace that with a speaker. So here's my speaker. It's a bigger speaker because I'm special. Take out the LED, replace it with a speaker. So here's one side of the speaker, here's the other side of the speaker. And it's not working. Not working because my wire broke. Okay, with the speaker working, unplugged, plugged in. There's my speaker. So with that, I can use the Piano Tuner app and pick up the frequency. Shows up as 97.6 Hertz. Alright, now that I have a single note playing, let's build a 4-key piano. When I hit the 4 buttons, I play 4 different notes. Now to do that, the wait loop determines the time or the frequency. The times that I want are 10 million divided by 2 times Hertz. So for 185 Hertz, N is 27,000, 24,000, 21,000, 18,000. In my wait loop, I've got 2 numbers that set the time, changing N to get close. These are the times that I want for A and B. So my wait loop here's A, here's B. This is the first wait loop. The wait loop that I call depends upon the button. Let's see, did I hit the first button? If so, call the first wait loop. Second button, called second wait loop. Third, fourth. Problem 6 looks at building a 4-key piano. What I want to do, play 4 different notes when I hit buttons. To do that, I'll use the previous code with 4 different wait loops. So, assuming the inner loop takes 5 clocks, this is the number of clocks between interrupts. Here's my scalars A and B. Those have to be integers between 1 and 255. Coming up with N, A and B that are close, that's what I wind up with. Other combinations work. My code is I'm going to check to see if any button's pushed on port B. If it is, toggle port C pin 0. I'll then set up the wait loop. If button 0 is pushed, call wait loop B0. 1 is pushed, call wait loop B1, B2, B3. And the wait loop is, here's your wait loop, and these are the constants A and B that set the timing. By changing A and B for the different wait loops, here's what I get. So the first button. Okay, so trying it. Here is the first note. That up so you can see it. 185.1, second note. To a 7.7, third note, 233.2, 277.2. So that's basically matching. You can also measure them using the Piano Tuner app. What you wind up with is the measured frequency pretty much matches what it should be. That's one of the beauties of assembly. I know exactly how long the program takes to execute. I can tailor the loops to be a specific amount of time. Throwing in a bunch of no-ops, I get the frequency more accurate. And that is homework set number 3 for ECE 376.